This video today is on molecular geometry, which is about the shape a molecule will take when it's actually floating around in the real world. So in our movie today, or our lecture, we're going to talk about the valence shell electron pair repulsion theory, otherwise called short for short VSEPR theory, and we're going to learn how it can be used to look at a Lewis dot structure and then determine what shape that Lewis dot structure will become in 3D. And the shapes that we're going to learn about are linear, bent, tetrahedral, trigonal planar, and trigonal pyramidal. As we talked about in previous lectures, we know that the Lewis dot structure format of looking at a molecule is a flat blueprint, and we can look at the different atoms that are in the molecule and how they're bonded together, whether those bonds are single, double, or triple. We can also look at the bonding electrons that are within the atom and the non-bonding electrons that are outside around the edges of the atom. And all of that information can be used to figure out the shape of a molecule. In the real world, however, molecules are not just flat, they're three-dimensional, and they're always wiggling and spinning and rotating, so their shape is very important in terms of how they work. So the molecular structure is what we're going to be learning about this week. It's the three-dimensional geometrical arrangement of the atoms in a molecule. And the 5 shapes we're going to learn about are named as linear, bent, tetrahedral, trigonal planar, trigonal pyramidal. Those are the 5 different shapes. The VSEPR theory, again, it's valence shell electron pair repulsion, explains how a molecule's geometrical shape is caused by the repulsion between the bonding and non-bonding electron pairs that surround the central atom. This should make sense because we know that electrons are negatively charged. And if you have negatively charged electrons in one bond, they are going to repel or push away the negatively charged electrons in the next bond. So, for example, water has 2 bonds, and those bonds are going to be pushing each other away, causing the molecule to have a certain shape. The non-bonding electrons are also important because they are also pushing on the bonding electrons and on each other. So in water there are 2 bonding pairs and 2 non-bonding pairs, which are going to force the atom to be a 3-dimensional shape. It won't sit flat on the paper. So this electron pair repulsion is going to cause the bonded atoms to move as far apart from each other as possible around the central atom, and this is going to cause the molecule to be contorted into a shape, and there's different angles between the atoms, and that defines what the different shapes are. So your job is going to be to determine the molecule's geometrical shape. First thing you're going to need to do is to draw the molecule's Lewis dot structure. If you need notes on that, please refer to the previous lecture. Secondly, you're going to count the number of high electron density areas around the central atom only. We're not going to count non-bonding electrons on the non-central atoms, so on the outside atoms, because they are not going to be determining whether the atom is a certain shape or not. So you're going to look at each number of bonds around the central atom, so single, double, or triple bonds. They all count as one high electron density area, or one area where there is a lot of electrons that are densely packed together. Each of the non-bonding pairs of electrons on the outside, or on the inside, on the central atom also count as one high electron density area. So once you've counted the total number of bonding and non-bonding electrons, or these high electron density areas, you're going to use geometry to separate each area as far as possible around the central atom. So for example, in a molecule that makes the shape that is bent, if you were to do, for example, we had talked about H2O, in its Lewis dot structure it would look like this straight line where you have hydrogens on either side of the oxygen. There are 2 atoms that are bonded to the central atom, so each of these bonding pairs is a high electron density area. So here's 2 areas. And then a molecule that has either 1 or 2 non-bonding pairs on the central atom will be bent. In this case we have 2 non-bonding pairs. So we have a total of 4 electron density areas for water. And these 4 areas, again they are here, are going to push each other away. They're going to repel each other around the oxygen so that they are equally distant. And it ends up making sort of an X shape on flat paper when you draw it. but I'm going to show this to you in just a minute in 3 dimensions, and you'll see that these the molecule, it's not going to be a flat X. It'll stick out. So this is what a bent molecule looks like. It'll basically look like a V. Now if you have a straight line Lewis dot structure that has 0 non-bonding pairs, so for example carbon dioxide has 2 atoms bonded to the central atom, so here's one area of high electron density and here's a second, and there are 0 non-bonding pairs on the top or the bottom of the carbon. So if there's a total of only 2 areas of high electron density, they're going to spread out as far apart from each other as possible around the central atom, which in geometry you can only take basically the biggest angle you can make between 2 atoms around a central point is 180 degrees, so it's a straight line because this is basically a 180 degree angle, and now these oxygens are as far apart as possible. So a linear molecule will only be made when their central atom has no non-bonding pairs. You can also have a molecule with no non-bonding pairs, and it can make a flat triangle. It will be flat on a paper just like the linear shape was, and it'll be flat because again there are no non-bonding pairs. So in this case you would have, for example, NO3 nitrate. It's T-shaped in its Lewis dot structure, so here's the T that we've practiced and we've seen in Lewis dot structures. Now if we have 3 atoms that are bonded, that means we have 1 area, 2 areas, 3 areas of high electron density. And these 3 are going to push away from each other equally, so you're going to end up having them spaced out roughly like 1/3, 1/3, and 1/3, or 120 degrees would be their bond angles. And this is flat because it does not have any non-bonding pairs on the central atom. So this molecule would be flat on the paper. All of these atoms would be in the same plane, hence the name planar trigonal. Trigonal is referring to the fact that this makes a triangular shape. Planar is referring to the fact that it is flat. It will not stick up. If you held it in your hand, it would stick flat on your hand. If you had a trigonal shaped molecule that did have non-bonding electrons, they will then take those flat atoms and push them down to make a pyramid. So a trigonal pyramidal shape is where you have a T-shaped Lewis dot structure molecule such as NH3. So again we have our T-shape. And so you are going to have 3 bonded atoms. So you're going to have 1, 2, 3 areas of high electron density in addition to the 1 non-bonding pair. So in total there are 4 areas of high electron density that need to spread themselves out around the central atom. And we can see this, sometimes it looks a little bit like an X, but what it's trying to show is that you have the nitrogen is sticking up and these 3 hydrogens are pointed down. These ones in the back are pointed slightly backwards. This one is pointed forwards towards us, and the lone pair of electrons are sitting on top like a hat. I'll show this to you again in a minute in 3 dimensions. We'll rotate it so you can see how this looks. Finally, our last shape is tetrahedral. Tetra means 4, as you've already learned, so this is a good one to remember that it's something that has 4 bonding pairs. So a tetrahedral molecule will look like a cross shape in its Lewis dot structure, as we can see here. There's 4 atoms, which means there are 4 bonding pairs. There are no additional non-bonding pairs, and this is because of the octet rule. And if there's 4 non-bonding pairs, again, these 4 areas of high electron density are going to spread out as far as possible. And this is very similar looking to the last picture. This is very similar looking to NH3, where there are 3, there's like a tripod on the bottom and lone pairs on top. Here in the CH4 we see the tripod on the bottom, however the 4th atom is on top. So the tetrahedral is actually sort of the root shape for most of these 5 shapes we're going to look at. Sometimes we just don't see all 4 atoms of the tetrahedral. So for example, the trigonal pyramidal is still a tetrahedral shape with 4 areas of electron density, but there's not an atom attached to these non-bonding pairs, so we only see the bottom pyramid. Even if we go back to our water example, these 4 are still making that tetrahedral shape with the 4 areas of electron density. However, we only see the 2 legs in the pyramid. There's no the other leg that would be sticking out is a non-bonding pair, and there's not an atom attached, so we would not see that. So these are our 5 shapes. For more complicated molecules that break the octet rule, there are many more shapes, as you can see here in this picture. There's ones that are called seesaw, an octahedron, all kinds of interesting different shapes for molecules that break the octet rule. So we're not going to cover them now. You might learn them in AP Chemistry or if you take chemistry in college. Now I want to give you a chance to look at the 5 different shapes that we just talked about in 3 dimensions. Let's look at the easiest of the 5 shapes. This is an example of carbon dioxide, and we can see that there are no non-bonding pairs on the central carbon as I rotate this in 3D space. And so it really is a flat planar molecule. As we said, the oxygens are 180 degrees from each other, and we can see that when we look at the molecules being flat. So this is a very simple molecule. Now if we look at a molecule of carbonate, this is a trigonal planar molecule. There are no non-bonding pairs on the central carbon if you made its Lewis dot structure. And so you can see this molecule is flat. It's hard to get it to be flat in the plane. I'm trying to make it flat, but you can see that all of these oxygens are in the same plane. They're in the same line as each other. So this is trigonal planar. It's trigonal because there are 3 oxygens which make a triangle around the central atom, and it's planar because all of the oxygens are in the same plane as each other and flat. Now the next 3 shapes all come from this basic tetrahedral geometry. This is a tetrahedron. So a tetrahedral. When we oftentimes when it's drawn, and as it was shown in the notes, it looks like this, where you have a tripod on the bottom and one on top. But as you rotate it, you can see that all of the hydrogens are evenly spaced. As this rotates around the carbon, you can see that they're all evenly spaced around each other. So it doesn't matter which hydrogen is on top, they all make that pyramid shape. And we can also see that the hydrogens on the bottom are more of a pyramid instead of flat because we can't see all 3 of them as it rotates. So if one of these, instead of there being a carbon with 4 atoms bonded to it, if one of these atoms was a non-bonding pair, then let's see what that shape would make. For example, NH3 has the tetrahedral geometry, where here we can see that we have the tripod on the bottom, and whereas in CH4 there's the 4th atom on top. This is the tetrahedral shape without an atom on top with a non-bonding pair. So this one is trigonal pyramidal or pyramidal. It's trigonal because again the 3 hydrogens around the central atom make it a triangle shape, but it's a pyramid because we can see that these hydrogens are sticking out. It's not flat in a plane as the other one that I had showed you. The other one I'd showed you, I could rotate it so that all the hydrogens were in the same line as the N, but I can't do it this way. So you can really see that they all make a, it's like like I said, like a tripod or like a little pyramid. And if one of those, now we have out of the tetrahedron, we took away 1 atom to make a lone pair. Let me take away 1 more atom, so all we do is have 2 atoms and 2 non-bonding pairs. And water is a perfect example of this. As we saw on the Lewis dot structure from the notes, there were the 2 bonded hydrogens and 2 non-bonding pairs. Those non-bonding pairs are going to push the hydrogens down to make an overall tetrahedral shape, but this is all we see. So we see this is a bent molecule because the non-bonding pairs are making this a tetrahedral. So I want to leave you with this set of practice problems that you can pause and record and write down and have those to work on. And as always, I've provided the answers for you. Good luck!